Hello guys, in this video I am going to talk about the intensity and potential near a uniformly charged wire. The wire may be finite or infinite. I am going to take on both the cases. The wire or the rod or the thin cylinder is having uniform linear charge density lambda equal to Q upon L. So lambda equal to Q upon L, and that is constant, linear charge density. The wire lies in the XY plane. The wire lies in the XY plane. First of all, I take the case of a finite wire. So lambda constant here. The point P is here. And the point P, if I drop a perpendicular from P on the wire, that is perpendicular distance is A. From P, I join the upper end, I join the lower end, I join the upper end, I join the lower end. Well, that angle is alpha and beta. Now, normally to get the expression for the intensity at P, we'll have to resort to integration by taking a small element dq, that will be lambda times whatever dy, and then I integrate over the whole wire the contribution of that, and then we arrive at the result. But in this video lecture, because it is for the IIT and the medical aspirants, I'm not going to do all these derivations. That will go into my scheme of basic lectures. So here we are mainly interested in the concept understanding. So at the point P, the intensity will have x compo Ex and the y compo Ey, and the resultant field is E, which makes an angle phi with the x-axis. That's it. Ex after integration, of course, will come out to be k lambda upon A into sine alpha plus sine beta, and Ey will come out to be k lambda upon A cos alpha minus cos beta after the integration. And then the resultant field E at P magnitude is Ex square plus Ey square root of that, and the tan phi is the angle that the resultant field at P makes with x-axis, that is tan phi equal to E phi upon Ex. Therefore phi is equal to tan inverse Ey by Ex. Here you are. So this is for the finite wire. Let me now talk about infinitely long. So this wire, suppose it is infinitely long, and the point P is of course close to the wire. I drop a perpendicular from P. That perpendicular distance is A. Once again, it is A. And now if I join P to the upper end, alpha would be 90. To the lower end, beta would be 90. So for the long wire, alpha and beta are 90. So Ex would just then become 2k lambda by A, and Ey gone. So this is 2k lambda, only Ex stays. So that is 2k lambda by A, and it is along I cap. The resultant field is along I cap. There you are. So 2k lambda upon A I cap. You can keep this result because this you can use it later on in many other problems of electrostatics, finding the maybe the capacitance of a cylinder or so many other things that you can make use of this expression. Let me now talk about the potential difference between 2 points near the long charged wire. Near the long charged wire. So for that, I use the expression E is equal to minus dV by dx, assuming that the perpendicular distance at x from the wire. So it will be, because E is a function of x, E is a function of x, and so is V. So E is equal to minus dV by dx. Integrate. I take dV equal to minus E dx and integrate both sides. And suppose I've taken the 2 points P and S. P is distance A, perpendicular distance A from the wire, and S is perpendicular distance B. So the limits of integration will be x equal to B to A, standard relationship between potential difference and intensity. So left side, straight away integration would give me VA minus VB, and on the right side I get minus 2k lambda dx upon x integral, and the limits are B to A. I interchange a minus sign, I make plus, so the limits get interchanged. So it is 2k lambda log of x to the base e, because dx upon x is log x to the base e. I put down x equal to b minus x equal to a. I get the answer VA minus VB equal to 2k lambda into log b to the base e minus log a to the base e. I take one special case of intensity near the end of a long wire. Now suppose this is a wire and it is very long, infinite long, very long wire, and this is the point P. This is the point P close to the lower end of the wire. Then in that case, once again, if I do the integration process, the resultant field comes out like this, making an angle 45 degrees, with x-axis, and the value of this E, remember the concept, root 2 k lambda by A. As usual, k in all these expressions is the electric field constant. K is equal to 1 upon 4 pi epsilon naught. So this is one conceptual understanding of the electric intensity and potential near a finite charge wire and a long, thin charged wire. Well, now I take the case of a full charge ring and then half ring and then quarter ring, and we'll try to work out the intensity, the field value at the center of the ring and at some other points. First of all, let me take the case of a charge ring. Our ring is in the YZ plane and the axis of the ring is along x-axis. So YZ plane and x-axis. The ring is uniformly charged, linear charge density lambda, charge q spread over 2 pi r. So lambda equal to q upon 2 pi r, which is a constant. This is spread all over. Now, if I want to find the potential at the point O, O is the center, then for each element dq, lambda into, well, whatever, dq, I integrate all, so it will be kq by r. So potential, electric potential at O will be kq by r, and potential at P. So every element is at a distance x square plus r square under root to the power half. So Vp will be, and when I integrate, so Vp will come out to be kq upon x square plus r square to the power half. Let's talk about the intensity. I can jolly well do the intensity because potential is a function of x. So I can take its negative derivative with respect to x and I get the intensity. But I can also do by the integration process. But once again, I've told you all the derivation processes I'm not going to take up in this video, because these derivations and definitions and all the basic things that will go into my basic lectures, not in these conceptual lectures where I'm targeting mainly the IIT and the NEET aspirants. So E naught, every element has diametrically opposite the same element, the fields cancel and I get E naught at the center 0. Field at the center of the ring is 0, and at a point P on the axis where OP is equal to x, it becomes kqx upon x square plus r square to the power 3 by 2, and the direction of the field is along I cap, So that is about the field or the intensity at center and at a point P on the axis. Off axis we are not talking. Now E is a function of x. E is definitely a function of x, and from this expression we very well notice that when x is 0, E is 0, and when x is infinite, again E is 0, field is 0, intensity is 0. That means somewhere between the center and infinity on the axis, the field will be maximum. To find that maxima, I use the standard mathematical procedure. I take the derivative of E with respect to x and put it equal to 0 and then obtain the value of x. I do that. So I take the derivative of this dE by dx, put it equal to 0, do the mathematics, I get the answer x equal to r by root 2. This means the intensity will be maximum, the intensity of the ring, charge ring will be maximum at a point r by root 2 from the center on the axis. I put the value of x equal to r by root 2 in this expression. I get a neat answer q upon 6 root 3 pi epsilon naught r square. Q upon 6 root 3 pi epsilon naught r square. Of course, I have broken k as 1 upon 4 pi epsilon naught. The mathematical part I am not going to do in this video lecture. The aspirants, you have to do it yourself, and that will go as a good practice for you as well. So this is the E max at a distance r by root 2. I show that on the graph. I plot a graph of E versus x. So when x is 0, field is 0. When x is equal to r by root 2, E is maximum, and the maximum value is q upon 6 root 3 pi epsilon naught r square, and after that again it falls, and finally it will become 0 when x approaches or x is equal to infinity. X is equal to infinity. So this is the graph that shows the variation of V with respect to x. You can do an exercise for plotting the graph of V versus x as well. Well, V at the center is of course kq by r. On P it is kq upon x square plus r square. So then it will be, it'll rise, reach a maximum, and then it will fall again, because when x approaches infinity, again Vp will become 0. Do that as an exercise. I do one more little exercise for you, that is, what is the work done to take a charged particle having charge q naught from center of the ring to the point P. Center of the ring to the point P. Now mind you, the direction of the field of the ring is towards I cap. So it will give a push. So technically the field force or the field force of the ring will do positive work, but the external agent will have to do restraining work. So if it has to go slowly, the work done by the external agent will be delta U as usual. So that will be UP final position minus UP minus UO going from O. I just put the values. So it will be Q naught into potential at P, kq upon x square plus r square to the power half, minus potential at O, that is kq by r. I lift these expressions from here. I get the expression for W. But if I ask you what is the work done by the field force, the field force of the ring, then that is a conservative force, and the work done by the conservative force is minus delta U. So it will be UO minus UP. So if Q naught is positive, the conservative force is doing positive work, whereas the work done by the external agent to move Q naught slowly would be a negative work. So the work done by the conservative force is UO minus UP. So that is Q naught into potential at O, kq by r, minus potential at P, kq upon x square plus r square to the power half. Now one more important thing that we talk about, the oscillation of a negative charged particle on the axis of the ring of a positively charged ring. That I have done already in a lecture, in a video lecture. I don't remember its code, but you can, all those students who are my subscribers can go through my library. I have put a full video on explaining that, so you can see that. So this whole part, oscillation of the negative charge particle in the field in the field of a positively charged ring, I am not discussing in this because it has already been taken up in a previous, I think it is ES 13, I think so, but you can check it up. You can check it up from my video library in the YouTube. Okay, now I also give you the concepts for the electric intensity due to half ring and a quarter ring. First of all, the half ring. So the total length is pi r, total charge is q. So lambda again, once again constant, q upon pi r. So at the center of the ring, once again by simple process of integration, you can do that. As I told you, derivations I am not doing in this video lecture. So O, EO arrow will be 2k lambda by r and I cap. So EO vector will be 2k lambda by r I cap. Okay. I do for the quartering. Potential will be easy because V at O will be just K Q upon R, because every element is at a distance r from here. So I have not written that, but potential, you can do it yourself. I have anyway spoken that in my lecture here. For the quarter ring, the length of the quarter ring is 2 pi r divided by 4. So the charge Q is distributed over 2 pi r divided by 4. So lambda becomes 2q upon pi r. So once again small element and then the integration. So the field at O comes out to be EO, and it makes an angle of 45 degrees with the x-axis, where E naught is root 2 k lambda by r. Potential, of course, potential for every element, so potential will be kq upon r as usual. I don't have to do that, it's just a very simple exercise. So this is for the full ring, the half ring, and of a uniformly charged disk. There is a disk of radius r, capital R, and the plane of the disk lies once again in the YZ plane, YZ plane. Of course, the axis of the disk is along x-axis. The disk is uniform, this face of the disk is uniformly charged with charge Q, so that it has uniform surface charge density sigma, that is Q upon pi r square, and that is constant. I take a point O, of course center of disk, and I take a point P at a distance x from the disk. Once again, the integration process and the derivations, I am leaving that because this is only for the concepts, for the conceptual understanding, mainly for the IIT and the NEET aspirants. Derivations and all that, I've been saying that again and again. I'll be taking on a whole series of basic lectures where I will do that. So here you are. So electric intensity at P, after doing the derivation, the process, the integration process, comes out to be sigma upon 2 epsilon naught into 1 minus x upon x square plus r square to the power half. Now, if x is much less than r, that means I am taking a point very close to the disk, then this x can be nearly neglected. So I can have sigma by 2 epsilon naught. Because here x would be neglected, x is very much less than r, so this will go, and r is very much, so this whole thing can go. Because r is very much bigger than x, so the denominator is too big for this, and I get the answer sigma by 2 epsilon naught. And this you have done, if you remember, in the application of Gauss's law. Of course, in my series of basic lectures, I'll be taking on the applications of Gauss's law, where I will prove this with the help of Gauss's law also. Now we talk about the potential. Again, the potential eventually at P comes out to be sigma by 2 epsilon naught into x square plus r square to the power half minus x. For points close, when x is very much less than r, so x square will be neglected as compared to r square, so this will become r and minus x. So sigma by 2 epsilon naught r minus x. Now I just want to remind you that in this lecture I should have also taken two very important bodies, charge bodies, that is surface charged conducting sphere and the volume charged dielectric sphere. But just as a reminder, now those of you who are subscribed to my channel, they can always have an access to my video library in the YouTube. Remember, you can note down, I have noted down that for you, ES4. In the ES4, I talk everything about the conducting sphere, everything about uniformly surface charge conducting sphere. And ES9 is for the uniform volume charged dielectric sphere. There is a full discussion of conducting sphere and dielectric sphere in these two video lectures, ES4 and ES9. Then in ES14, what I told you, in the ES14, I have discussed the SHM of a negatively charged particle on the axis of a positively charged ring. That is why I did not take up that in this lecture is VES16. I hope you have enjoyed the lecture. Subscribe my channel and keep on getting all these videos from me. Thanks for watching.
If you love the video and want me to make more useful videos for you, subscribe my channel and hit the bell icon to stay updated.